going to be talking about deductive reasoning. To solve any geometry problem, we're going to use deductive reasoning to take a given statement, also called a hypothesis, and draw a conclusion from it. For example, you might be given two triangles and asked to prove that they are the same or similar. Or you may be given a square and asked to show some of its properties. Or you may be given a circle and a line and show how they interact. Whatever the question, whatever you're being asked to show or prove, our job is to use deductive reasoning, taking a statement and drawing a conclusion. Deductive reasoning is built on something called conditional statements. These take the form if A, then B. So we take a statement and draw a conclusion. A is our hypothesis, B is our conclusion. The example I'm going to use in this video is, if I mix red and blue, then I make purple. We can play with conditional statements in a few different ways. The first way we're going to play with it is called the converse of a conditional statement. This is when we switch the hypothesis and the conclusion. So we switch A and B. Using our original example, if I mix red and blue, then I make purple, the converse of that statement would be, if I make purple, then I mix red and blue. I've just switched my hypothesis and conclusion. There's a classic example of a converse in Alice in Wonderland. The dormouse claims, when I sleep, I breathe, which is true. But then he says, when I breathe, I sleep, which may be true for the sleepy dormouse, but isn't true for the rest of us who like to breathe and be awake sometimes too. So a converse, you notice, does not need to be true just because the original statement is true, as in the dormouse's example. It is merely switching A and B. We say that this means the converse is not logically equivalent to the original statement. Being logically equivalent means if one statement is true, then the other statement must be true, and if the one statement is false, the other statement must be false. A converse is not logically equivalent to the original statement. The next way we can play with a conditional statement is called the inverse. This is where we negate the hypothesis and conclusion. If not A, then not B. So using our example, if I mix red and blue, then I make purple. The inverse statement is, if I do not mix red and blue, then I do not make purple. Just like the converse, the inverse is not logically equivalent to the original statement. So it does not have to be true just because the original statement is true. The last way that we can play around with our conditional statement is called the contrapositive. This is where we switch the hypothesis and conclusion and we negate them. It's like a combination of the inverse and the converse. If not B, then not A. Using our example, if I mix red and blue, then I make purple. Our contrapositive would be, if I do not make purple, then I do not mix red and blue. The original statement and the contrapositive are logically equivalent. If the original statement is true, then the contrapositive is also true. And if the original statement is false, the contrapositive is false. Take note here. This means that the inverse and converse are also logically equivalent to each other, although they're not logically equivalent to our original statement. This is because they're contrapositives of each other. This is pretty neat, and all of this becomes very useful in our future geometric proofs. Here I'll leave up a summary of our conditional statements and the different ways we can play with them. The green statements are logically equivalent, and the yellow statements are logically equivalent. Thank you for watching, and I'll see you in our next video. We'll talk about what a proof is and how we use it to solve our geometric problems, and we'll discuss theorems, postulates, and definitions.